Okay, so let's make another video. So today's Friday. There's a quiz today. So normally on a Friday, because we always have quizzes on Friday, I wouldn't say too much because we need time for the quiz. So I won't say too much today either. Um, but I will talk about. I'm going to go back to something that I skipped at the time out of chapter 5. So I'm going to ask you to recall, because I did cover section 5.4, which was this, if you remember, it was like second order differential equations that come from springs. That there was the damped case and the undamped case. Like we had a picture like this. There was a mass and a spring. And in the damped case, we had this dash pot. In the undamped case, we had no dash pot, or we could say we had a dash pot that just wasn't doing anything. It was applying zero force. Um, so if you, hopefully you all remember that. I will kind of re-derive at least the relevant part that we're about to do. So we're going to talk about the undamped case first of all, so that makes things a little bit easier. Maybe I'll make a short comment about the damped case at the end if I remember. But so right. By the way, this derivation is in the book. I started kind of showing a little bit extra work that the book doesn't show, and then I ended up writing a full page of stuff. So now I'm just going to talk about the page that I wrote. Um, so recall Hooke's law about a spring, which is the force exerted by the spring is negative k times x. Of course, x is the displacement from the natural spring length. Like if nothing was pushing or pulling on the spring, it would be however long it is. And x is the difference between its current length and its natural length. Now, when we were in section 5.4, there was no external force. And now we're going to say that there is an external force. That's why this is called forced oscillations. Um, we're going to be pretty specific about what form of external force we're interested in. We're interested in a periodic, in fact, even more specific than just a periodic one. It's a cosine function, an external force that's of the form of a cosine function. And I guess there is reason for this. This is a particularly important type of function. There's a lot of natural examples where you have such a force applying on the mass, just going back and forth in this periodic way that is like a trig function. Um, so, right. We look at the total force. Of course, force is mass times acceleration. So the position of the mass we can call x, or at least if we measure the position relative to like where the mass would be if the spring was at its natural position, we can represent the position as just x. So acceleration would be x double prime, so force is mx double prime. And so what is the total force? First of all, there's the force of the spring, and then there's the external force. That's it. And I move some things, well, just one thing to the left, and I get this, which this is a second order linear non-homogeneous, because this is not zero, differential equation. And this is very similar to what we dealt with in 5.4, except it was homogeneous. There was no external force, so this was zero. So how would we solve such a thing? First, we would find the complementary solution, which is the homogeneous part. So actually finding the complementary solution is just like what we did from 5.4, but for people who don't remember, because it was a little while ago, and actually I didn't remember, we write down the characteristic polynomial for this homogeneous part, which is mr squared plus k equals 0. I solve this for r. It's easy enough. I get this. This is a square root of a negative, so this is going to be an imaginary number. So plus or minus square root of k over m times I, and we're going to call this number the square root of k over m. We're going to call that omega naught. So what would we get when we have an imaginary solution? Of course, like the real part is 0, so I have an invisible e to the 0t here. But other than that, I would just have a cosine of the imaginary part times t, and then a sine of the imaginary part times t. Right? That's what we do when we have complex roots for this. Okay, that's the complementary part. We should also find a particular solution, so here we use the method of undetermined coefficients. I look here, I see cosine omega t, so I should guess that my particular solution takes the same form, so maybe it should involve a cosine omega t. But if you remember, when we're doing this, sines and cosines go hand in hand. So if I have a cosine omega t, I should probably also have a sine omega t. In the book, they just skip this part. And in fact, we are going to find, in the end, we are going to find that b is 0. But I like to have that there, just because I don't think it's entirely that easy to see that b should be 0 just from here. We'll do the work to show that b is 0. And by the way, at this point, and this is another point that the book doesn't seem to mention, we are assuming that omega is not the same as omega naught. And I'm going to make a comment about this at the end, but just real quick, if omega and omega naught were the same, we would have a problem. These would be duplicate solutions, and then I would have to multiply by t. And well, that wouldn't be that big of a problem. It would just be different. So we're assuming that's not the case. So I don't have to do that. I don't need t's here for the time being. So let's proceed under that assumption. How do we make this work? I need to plug it in here and make sure it equals that, right? So I'm going to need the second derivative. And here I just jumped straight to the second derivative. I don't think it's that hard. If you like, you can fill in the first derivative beforehand. But second derivative of cosine is just negative cosine. And since I have this omega in here, I would have an omega squared. And similarly, the second derivative of sine is negative sine. And since I have this here, I would have this here. So I go here. I do m times x double prime plus k times x, and I didn't want to deal with a huge mess, so what I did was I factored everything, like xp double prime is this, xp is just this, and they have the common factor, like a cosine omega t plus b sine omega t. So if I'm doing m times this plus k times this, I should get this with the common factor of a cosine omega t plus b sine omega t. And that should equal that, right? And now here we line up our coefficients. And here is where I can see that b is 0. Because on the left, I have a sine term, and the coefficient of sine would be b times this. But on the right, I don't have any sine term at all. So the sine terms on both sides should just be 0. So b should really be 0. For the cosine term, on the left, I've got a times this, and on the right, I've got f naught. In other words, a should be f naught divided by this. So that's what I wrote here. And then I just simplified. I wanted to get the same answer that the book got, and it is the same answer that the book got. I just wanted to make it look like that. And this is just some simple algebra. I guess I divided the top and bottom by m to get here. And then, if you remember, omega naught is the square root of k over m. So this thing is omega naught squared. So I replaced it. And this is the answer that the book got. So if we put that together, I get, so here's the complementary solution, here's the particular solution, and there we are. So one thing to notice about this, because this section also has the word resonance in the title, and we sort of touched on resonance, well, maybe it was yesterday, maybe it was definitely this week, but this thing has omega naught squared minus omega squared in the denominator. So if well, okay, I'm going to say something, so maybe formally this doesn't make a lot of sense. This wouldn't be defined if omega naught was the same as omega. I mean, we would be dividing by 0. Of course, we're assuming that omega naught is not the same as omega. So maybe that shouldn't bother us because it's definitely not the same. But what should bother us is it might be close. The omega naught might be very, very close to omega, in which case we're not dividing by 0, but we are dividing by a very small number, which makes this blow up. So we would have this huge number times a cosine. So this cosine is, of course, a periodic function, and this is giving you the amplitude. So this can give you a huge, huge amplitude. And we use the word resonance to sort of just generally describe the phenomenon of like what happens when this is close. So, right. The next thing, let me show you in the book where this is. This is like, so we just kind of derived this stuff. Now I'm on the next page under what the book describes as beats, and it says, suppose we impose the initial conditions, blah. Let me actually show the work for that. It's not too hard, but I am going to take the answer that we just got and impose these initial conditions. So if I put in 0 for t, first of all, cosine of 0 is 1, sine of 0 is 0. So I would just get c1, this goes away, plus this times 1. And x of 0 should be 0, so I set that equal to 0. Oops, we're blurry. So I set that equal to 0, and then I can solve for c1. X prime of 0 should also be 0. If I do x prime, I should get this, right? Yeah. And then if I put in 0 for t, sine of 0 is 0, so this goes away. This stays, so C2W, or C2 omega naught, and then this goes away. And so I get C2 equals 0. Blurry again. Yeah, and so then I plug everything in. So let's see. C1 was this, C2 is 0, and then I can factor this number out of everything, and I should get this. So, right, let me just then say a few words about the nature of this solution. And again, what happens when omega naught and omega are pretty close. So first of all, obviously this number blows up. But what happens to something like this if I'm doing cosine of omega t minus cosine of omega naught t? We see, let's see, well, I can just show you the book. A graph sort of like this. So in the book, they use a trig identity to take this and transform it into line 10. So we have a product of two sine functions that have different periods. And the graph of such a thing tends to look like this. It's like you have a long period and a short period. And the graph is sort of jumping up and down, and the amplitude goes up and then down and then up and then down, like according to the longer period. So I mean, here's sort of another picture. I'm just on Maple. As you can see, I told it to plot cosine t minus cosine of 0.99 t, just because 1 and 0.99 are very close. I'm just using that as an example of an omega and omega naught that are very close. And I plotted it, and it looks like this. Of course, maybe you wonder why doesn't this quite look like the picture we were doing. If I go, why don't I go from, instead of just 50, why don't I go to, say, 200? Oh, it's still on its way up. So the amplitude, like it's, yeah, it seems like it's just going to go up and up and up. Why don't I go farther? How about 500? Whoops, what did I change? There we go. We can see it on its way back down now. And actually, maybe I should have, I don't want to go too far. How about 1,000? There we go. At least now we can see like one full long period. But the long period is so long compared to the short period, but by the time I can see a full long period, the short period is just, I mean, it's just filling in the entire space with solid color. Like the graph is not really, it's hard to see what's happening. It's jumping up and down so frequently that it's not really visible. But that's the effect that's happening. Maybe, what if I changed it to numbers that aren't quite as close, like 1 and 0.9? Yeah, maybe that looks better. Maybe, well, it doesn't look better yet. Let me make the picture smaller. Yeah, okay, that's more reasonable. So here's the long period, and we can see there's many short periods in between, like happening in one long period. But at least, you know, the effect isn't so extreme that it's just filling it in with solid color. We can sort of see what's happening. Okay, well, that's neat. So let me say a word now about when omega and omega prime are equal. And I won't show a lot of work. I won't go into a lot of detail here. I'll just give an idea. Whoops. Great. Well, we are still recording, so whatever. Yes. If omega and omega prime were equal, I would have the t here, because once again, these would be duplicated terms. This would need to be adjusted, so I would need a t here. And I won't bother going through the work of figuring out what A and B would have to be in that case. They would be something. The point is, our particular solution would have the form, it would be a number times t cosine omega t, or t sine omega t. And what happens when I do such a thing? So this is another graph where, okay, yeah, sorry, this isn't a great view. If I go back, let me go back to the first one I showed you on top. Like this. This graph and the graph down here kind of look not too different. I see it's like wobbling back and forth kind of fast, and these wobbles are becoming more and more wobbly. Like the amplitude is going up and up and up as I go this way. And I would describe this much the same way. Maybe it looks like that this is moving faster, or maybe that's just because the scaling, this is only to 50 and this is to 100. But roughly speaking, I would describe them as looking kind of similar. But then once again, let me zoom back out to where I was for this one. Whoops, maybe more like 500. If I zoom out far enough, I can see this one on its way back down. When omega equals omega prime, and we have that t there, see, this is the graph of t cosine t, just an example of the type of function we would be dealing with if omega was equal to omega prime. It's like this, and I can try zooming out to hope that these amplitudes that are increasing, maybe they come back down, but they're not going to. You know, I can plot this all the way to 500, and it just keeps going. I can go to 1,000, and yeah, now the short frequency is so high that it's just filling in with solid color, and still I see the amplitude just going up and up and up. I'm sure you believe me at this point. If I plot it all the way up to 2,000, the picture looks basically the same. It's just like a solid triangle at this point. So yeah, I mean, maybe yeah, I don't really have to keep showing you this from different views. I'm sure you believe me. This is the type of function that like the amplitude just keeps going up and up and up. And this is why, if you think about like the physical example that we're talking about, this is how, you know, like that bridge, the one theory behind why this bridge in, I think it was Kansas, collapsed is because the wind was blowing at it at like the right frequency. It's sort of like if someone is on a swing and you give them a push, and then when they come back to you again, you give them another push, and then they go higher, and then they come back to you again, and you give them another push, and they go higher. If you're pushing them at the right frequency, well, of course, for a swing set, maybe this is a bad example because nobody's really ever kept pushing somebody until they, you know, spun all the way around the swing set or anything, or I hope not. But you can get someone going pretty high, like on a swing, and like even if your arms aren't really that strong. You just give them a little push. Next time they come back, you give them another little push, and it's at the right frequency, and this just builds, and they go higher and higher. Um, this is kind of like what's happening. And in real life, of course, there's physical limitations to this. I mean, we're talking about this thing. Eventually, if this is going back and forth so hard, eventually it's just going to bang into the wall. And our mathematical model for this situation is not intended for this thing to be banging into the wall. Um, so at some point, we don't really trust the model anymore. If the amplitude is so high that it's banging into the wall, for example. Um, but it's good enough up to that point. Um, so we shouldn't in real life. Nothing oscillates back and forth with an unlimited amplitude. Eventually, that mathematical model is no longer accurate. So something falls apart. But up to that point, it kind of behaves as predicted, roughly speaking. Anyway, I'll leave that for today, and I will upload a quiz soon.